Good afternoon, everybody. Thank you for joining the webinar. My name is Gabriela Bedravo. I am the project leader of the project Righweight. Actually, the project that is funding this webinar. The webinar will be divided in 4 parts. So the first part is to present what is Flanders Make and the Righweight project. It will be a 5-minute and short introduction. Then my colleague Ahmed El-Madi will talk about adhesive technologies and trends in circularity. And then after that, my colleague Jeroen Jordens will show how we use digitalization to improve adhesive bonding in Flanders Make. At the end of the webinar, there will be time for questions and discussions. We hope that you are there to discuss with us.
You're still on mute, Gabriel.
You cannot hear me?
Yeah, we can hear you.
We can hear you.
Yes. So I am on mute, but I am talking from the meeting room. So if someone cannot hear me, please check your audio. In any case, I will ask all the participants here to turn off the microphones and cameras while the presentation is ongoing. And please, if you have any questions, add them in the chat. If you want to ask the question in any way, you can raise your hand. And
Gabriel,
yes.
We don't hear you. You're still muted.
I don't know what the problem is, but I can hear you. So
yeah, I see. Yeah, apparently he has some problems with the audio. Yeah, sorry for that. So I hope you enjoy the webinar. Please keep your microphone and your cameras off during the presentation. So first of all, as I say, I will present a little bit Flanders Make. I am pretty sure that most of you already know Flanders Make, but the goal of Flanders Make is something that we have to be clear, is to bridge the gap between advanced research and industrial applications. So as you can see, most of our projects are involving universities and industry. So the whole goal here is to bridge the gap between both of them. We have many, we are driven by Industry 4.0 market trends. We are working in smart and interconnected products. We want to reduce the time to market of products and produce customized products at the same price of serial production. Agile and resilient people-centered in manufacturing. So we want to help the people to work in a better environment. And now on, we are also working on sustainable products. And we are putting emphasis on sustainability on all what we are developing. Flanders Make is quite a big of an organization right now. We are all over Flanders, and we are about 750 researchers working there. We are in collaboration with all of the Flemish universities. Yeah, so the kind of services that Flanders Make can support are research. So this is a research project, but we are also support the custom partners and industry by customized innovation. So if you have specific required that needs or expertise, you can come to us. But also you can also ask Flanders Make for the use of the laboratory, so we can provide with testing and validation facilities if needed. So this is something that is important to keep it in mind. So Flanders Make is here to help companies to achieve results and to innovate their products. In this specific project, we have some interest. Our goal is to create lightweight solutions, and we are going to target 5 different areas. So we are analyzing how to improve the material supply and development, how we can better characterize those materials to have better designs, design and smart functions, so we can add better designs and better products. How we can improve the manufacturability and the manufacturing processes and the recycling of the production. Today, as you will see, it will be really centered in the last two parts, but in general, this project is tackling all of these 5 aspects of the lightweight design. We are not alone in this project. We have several partners. We have from all over this region in Europe. We have IPEC, IMAST, and cluster business centered partners. So how we help in this project? In general, in this project, we have two kinds of participants. We have in one side champions that are big companies that define challenges, existing challenges that are blocking them to provide lightweight solutions. And in the other side, we have SMEs that bring new solutions to those challenges. In general, the SMEs that are joining this project are bringing low TRL solutions, and the goal of the project here is to help them through our thematic environments and our labs to develop their solutions to a higher level. So ideally, they will arrive with a low TRL, let's say 4 TRL solution, and they have to achieve at least a TRL 7 solution at the end of the project. So how we help them? So first, as a summary of the project, the big companies define technical challenges. What are the problems that they are facing to create lightweight solutions? Then we provide support to SMEs to innovate their solutions to meet the challenges imposed by the big companies. And then we have demonstrators where we show how these technologies developed by SMEs are useful, and ideally they can be exploited by the companies in the future. But also the last part, and that's not the less important, is we are providing with education and coaching to all the SMEs and people in Europe to create lightweight materials and solutions. And part of those coachings are those webinars. And today you will see Ahmed will present the part of the bonding and the bonding techniques. So Ahmed, the floor is on yours.
Right. So thanks, Gabriel. Also from my side, I would like to welcome the audience of this webinar. My name is Ahmed Al-Mahdi. I'm a research engineer and European adhesive specialist working at Joining Materials Lab at Flanders Make. And in the next few slides, I'm going to give you an introduction to the adhesive joining technology. So adhesive bonding is basically joining two parts together with an adhesive. And this technology is widely available in many applications. You can see it in transportation sector, for example, for bonding of windows or windshields. You can also see it in energy sectors with bonding of wind turbine blades. And they are extensively used in construction as sealants, as a bonding of floor tiles, for example, and also in crafts and packaging. We can see a lot of advantages in using adhesives compared to standard mechanical connections and welding, for example. We can see, for example, that the load transfer of adhesive joints is much more uniform compared to standard bolts and nuts connection. And the discontinuities and stress concentrations that are resulted from opening holes in the material are simply reduced. This is also important when you are considering bonding of special materials like composite materials or glass, for example. Adhesive joining also gives more functionality to your joint. So, for example, you can add sealing function, you can add flexibility or vibration damping into your adhesive joint. Adhesives can also be used to virtually bond all materials, including dissimilar materials. Of course, you gain a lot of weight reduction by the removal of typical fasteners and bolts and nuts in general. And finally, you can also bond very small areas, but also very large areas seamlessly with adhesive joining. But with all these nice advantages, there are also some challenges and limitations for adhesive joining. in general, adhesives are materials that have limited resistance to high temperatures, as you can see from the curve up top. A typical epoxy adhesive, for example, can reach maximum strength at around room temperature, as you can see, but at 100 degrees, for example, they have much less strength. Adhesive joints also tend to age with time and environmental conditions. As you can see from the second curve, you can see that temperature and humidity can significantly reduce the strength of a joint. Of course, with proper design of the adhesive joint, these risks can be reduced. In addition to that, the adhesive joining process itself is complex and it needs specific preparation and surface treatment requirements. That also adds to the complexity of the process, as we will see later on. Also, adhesive joints in general are difficult to debond once they are cured. But in the second part of the webinar, we will see some solutions on how to make debonding possible. Finally, the adhesives and associated cleaning agents are considered hazardous material. So all these materials, they would at least bear one of these safety pictograms that you see on at the bottom. But of course, if you follow the correct safety procedures, you can reduce the health risks involved. Now, if we take a look at the adhesive joining process, we can divide them into 5 main steps. The first step is part preparation and conditioning, where you bring your parts and your adhesive to room temperature, and you check if they fit together, if they are cleaned, for example, and if they are fit together. Then you move to surface treatment, where the surface is cleaned and treated to be ready for bonding. Then the third step would be mixing your adhesive and dosing the correct dose on the treated surface. And then you apply the adhesive. The parts are then assembled together and fixed to prepare them for curing. And the final step would be curing of the adhesive to have the final bonded part. Let's dive quickly into each step in the next few slides. So first of all, we have to, of course, talk about adhesives. And adhesives are actually polymers. And these polymers are typically made up of resins and sorry, somebody stopped. Is there a problem with the audio? Okay. So these adhesives are actually polymers. And these polymers are made up of resin molecules and hardener molecules, and they can be classified into 4 main groups. First group is the thermoset group, which is characterized by being strong and brittle. An example of these can be epoxies, for example, polyurethanes, acrylics, phenolic adhesives, anaerobic and ultraviolet curable adhesives. Next, we have thermoplastics, which are tough and ductile. And these include hot melts, cyanoacrylates, plastisols, which are used in sealants, water-based and solvent-based adhesives. Third, we have elastomers, which are very flexible. So, and these are typically found in sealants such as silicones, silane modified polymers, which we call them SMPs for short, and also reactive hot melts. Finally, we have thermoplastic elastomers, which from its name combines both the properties of thermoplastics and elastomers. Now, if we classify the adhesives in terms of strength versus ductility, you'll see that epoxies, polyurethanes, and phenolics will come up top in terms of strength. So they will achieve the highest strength, but of course they have the least ductility. And on the other hand, silicones and SMPs will have the most flexibility in all adhesives, but of course they have lower strength. Here we have to note that there are some special chemical formulations which can give each of these types additional features. For example, epoxies, they are brittle, but there are certain chemical formulations, for example, like silane modified epoxies, which can give also some extra ductility. Here, the selection of the adhesive is generally dependent on the intended bonding application and also the type of the material you would like to bond. Next step in the adhesive joining process is surface treatment. And here the main objective is to improve the surface wetting and the long-term stability of your bond. This is done by increasing the surface energy of the part and have more spreading of the adhesive on the surface. In the figure up top, you can see an example of bad wetting. So here you can see that the adhesive is not spread on the surface. And this is because the surface tension of the adhesive is higher than the surface energy of the part. And in contrast, if you see the case where you have good wetting, the surface energy of the part is actually higher than the surface tension of the adhesive, and there you can achieve more spread on the surface. Of course, when we treat surfaces for bonding, our main goal is to remove any contaminations and expose the base material. So these contaminations can be, for example, oils, fingerprints, moisture from the atmosphere, also oxides and release agents if we are talking about plastics. So here, one of the or even the most important step in this regard is the proper cleaning of the part. And therefore, if we are talking about handling of cleaned and treated parts, we always recommend that you avoid touching the treated surface, or otherwise you will introduce some oils from the fingerprints, and then you will have bad quality bond. Surface cleaning in general can be done with cleaning agents or solvents. So for metals, for example, you can use organic solvents, acetones, or ultrasonic cleaning bath. But for polymers, we have to be a little bit careful because some of the solvents are aggressive to polymers. So we have to use non-aggressive solvents, such as, for example, isopropanol. For surface treatment, the three most used methods are grade blasting and sanding. That also improve the surface roughness of the roughness of the surface. Second is plasma treatment, which is very known for polymers. And the third would be applying primers and coatings as adhesive promoters to the surface that you would like to bond. Next step is mixing and dosing. So mixing is actually required when you have two component systems, or sometimes if you have one component systems with catalysts, such as the booster systems in one component polyurethanes. For these adhesives, you have to follow the exact mixing ratio that is recommended in the datasheet. Otherwise, you can risk having an incomplete curing. The mixing itself can be done with static mixers, as you see in the image, or with dynamic mixers for more continuous bonding work in bigger factories. Also, it is important to correctly calculate the dose that you need before you proceed into your bonding application. The reason is that incorrect dosing can result in too little or too much adhesive, which also can affect the final quality of your bonding application. Next step would be curing of the adhesives, or we also call it hardening of the adhesive. So curing is actually, here it means building cohesion strength in the adhesive, or in other words, changing the adhesive from a viscous liquid into a rigid solid. Curing can be achieved by many mechanisms, such as heating, cooling, humidity, and evaporation, as you can see. First, the curing by heating can be done either in the oven or at room temperature by the exothermic reaction between the two components of the adhesives. Examples of these are 1 and 2 component epoxies, 2 component polyurethanes, 2 component MMAs, and also phenolic resins. One thing to mention here is that 1 component epoxies, they always need heat to be cured, and they also have to be stored in refrigerated storages. Curing by cooling is typical for hot melt adhesives, where you simply cool the adhesive to room temperature from higher temperature. And this is very famous with, for example, the hot melt adhesives that you use for crafts and do-it-yourself. Other possibility is curing by humidity. So in this regard, the adhesive absorbs the humidity from the air to initiate the curing. And this is typical for 1 component polyurethanes, cyanoacrylates, and also 1 component silane modified polymers. Finally, we have adhesives that can cure by evaporating of solvents and water. And the example of these are very famous, the wood glue, or what is called polyvinyl acetate, and also solvent-based acrylics and polyurethanes. We also have special curing mechanisms for adhesives. For example, we have the anaerobic adhesives, which cures by the absence of oxygen and in the presence of metallic ions. And this can be found in thread locking applications, for example. Another method is sol gel curing, in which the adhesive changes from liquid to gel by absorbing plasticizers, and also in the presence of heat. And this is very typical for PVC plastisol adhesives, which are also used as sealants. Finally, we have adhesives that do not harden, so they don't need any phase change or any curing schemes, which are typically found in pressure-sensitive adhesives. Now, if we take a look at the curing time versus the final strength of the adhesive, we can see that the acrylics family in general, they achieve the fastest curing time. Acrylics family, that would be the cyanoacrylates, UV curing adhesives, and also the acrylics. They achieve the fast curing times, but also they give, or they are situated in the intermediate strength spectrum. Whereas if you look at polyurethanes and SMPs, for example, they have the longest curing times, but yeah, SMPs, for example, they give the lowest strength of the bunch. Here again, epoxies remain the highest of the strength of the adhesives, but they also have intermediate curing times. Here, one thing to mention is that there's no fixed curing time for adhesives. The curing time is dependent on the adhesive chemistry, the formulation of the adhesive, the environmental conditions, so the temperature and the humidity where you apply the adhesive, also the mixing quantities that you use, and the application itself, of course. Now we come to the adhesive joint design. So if you would like to design an effective adhesive joint, first we have to look at the adhesive properties. Brittle adhesives, for example, they can resist tension, compression, and shear loads, but they have poor performance when it comes to cleavage or peel stresses. So flexible adhesives, on the other hand, they can resist peel and cleavage stresses. So the general rule here is that if you have, or if you are using a brittle adhesive in your joint, let's say, for example, epoxy, then you have to design your joint to promote tension, compression, and shear loading, and minimize as much as possible the cleavage and peel stresses. If your main forces are peel and or cleavage stresses, then it's best to look in the direction of flexible adhesives. So now we come to quality control and testing of the adhesive joint, and this can be divided into two groups: destructive testing and non-destructive testing of adhesive joints. The most important tests for destructive testing of joints are lab shear test, peel test, and aging tests. Lab shear tests, they typically determine the maximum force that a bond can hold in lab shear configuration, while peel tests determine the resistance of the joint to peel forces. Both of these tests, as you can see, are well standardized in ISO and ASTM norms. Aging tests, they determine the long-term durability and performance of the joint in various environmental conditions, such as, for example, water submission tests or cyclic thermal and humidity tests. For the non-destructive tests of the joints, these are more to assess the quality of the bond. Yeah, for example, you can determine if there are any air gaps or delamination in the bond structures, as you can see from these little red arrows on the images. And the main or the most popular methods that are used are ultrasonic testing, where you can detect the change in media via ultrasonic probes, for example. And the other method is thermography, where you heat the adhesive joint slightly with a heating source, like for example the halogen lamp, and take images with an infrared camera. And yeah, the difference in the media between air, for example, and the rest of the assembly can be reflected from the heat transfer efficiency. One final point here is the qualification of the workforce. So of course it's important to have proper training of people who will be involved in your bonding solutions. Also, if you are working with certain standards like the DIN 6701, for example, these standards dictate that you have to have a certain level of training for the personnel involved in bonding. According to the European Welding Federation, there are 3 levels of qualification and certification in adhesive bonding. The first level, that's the basic level, which is the European Adhesive Bonder, and this qualifies the operators who will actually perform the bonding work. Second level, which is a little bit higher, that's the European Adhesive Specialist level, which qualifies the bonding supervisors and those people who will also draw up the bonding work instructions. The highest qualification level is the European Adhesive Engineer, which is more into decision making and also supervision of company-wide bonding applications. At Flanders Make, we collaborate with Lame Academy to deliver the AAB level, that's the European Adhesive Bonder level, in the Joining and Materials Lab here in Lommel. So we deliver the courses and the certificates in Dutch. So if your company is interested in training, please contact my colleague Yolanda Dams on this email that you see in front of you. So here, if your company is looking for implementing an adhesive joining in their production, what should you take into consideration? I tried here to list 5 main points as checklists, but of course it's not inclusive of everything. First is your application. You have to think in terms of your application. Is it feasible to use bonding in your application? Do I have to change the design of your application? Do we have to for example, look for surface conditions or the adhesive type that you will have to use? Second point is the production constraints and the production environment itself. What are the production leading times? What is the conditions on the workflow in terms of temperature, humidity? Do you have to change, for example, operations or material handling to adapt for the adhesive bonding process? Third point is you also have to look at the infrastructure and storage with respect to adhesive bonding. Probably you will need some mixing and dosing equipment. You will also need surface treatment equipment. You need ovens, for example, for curing. You will also need storage for the adhesives and also the parts. If they, for example, if they have to cure at room temperature, they have to store them properly in a storage facility. And fourth point is the safety and cleanness. You need to consider a bonding area that is free of dust and free of silicones. And also you have to keep in mind that you need to store flammable solvents and flammable adhesives in a proper way. And of course, the last point would be the proper training of people from bonder to engineer level. Now let's see how we can solve the challenge of debondability in adhesive joints. When we talk about debonding, that we basically mean separating of the joint parts, and this can be done in 3 ways. Either we cut into the substrate, which is of course bad for the substrate because then you cannot be able to use them later on, or you can have the debonding at the interface between the adhesive layer and the substrate, or within the adhesive layer. Of course, what we want to focus on is the 2 last methods where you can actually reuse your part afterwards after the debonding in that regard. So if we try to classify or think of ways to debond, we can group all the debonding methods in 3 main categories. First, you have the mechanical debonding, where you basically introduce a form of crack into your adhesive, and then you propagate this crack until you get the separation of the parts. The second method is thermal ways, where you can heat up your adhesive up to a certain, above a certain temperature, which we call glass transition temperature. And at this temperature, the adhesive can change from a solid, rigid glassy state into a rubbery state. The rubbery state has typically weaker mechanical performance. So if we apply force at this rubbery adhesive, then we can easily achieve debonding. The final method would be the electrochemical debonding methods, where you can, for example, use electric potential or UV light to induce debonding of the adhesive molecules. If you would like to translate these mechanisms into actual methods, how we can debond, then the mechanical methods would simply include pulling the joint, or shearing the joint, or introducing a crack in the joint. For thermal debonding ways, we can heat up the adhesive by convection, by induction, by microwave, laser, or infrared technologies. And in between the mechanical and thermal, we have the thermally expandable particles, which can be considered a mix of both, where you heat up the particles, you trigger the particles for expansion using heat, and this can also introduce cracks into the adhesive to cause debonding. The electrochemical methods can, from its name, of course, you can apply electrical potential or UV light, or with chemical solvents. From these methods, we focused on 6 of them that have very high market potential. And in the next few slides, I will quickly give you an overview of each of these technologies. Debonding by convection, that's the simplest debonding method, which is basically involving heating the adhesive in big ovens, for example, or just typical ovens, beyond the glass transition temperature, and then we apply mechanical force to have the separation at the rubber state. The potential of this method is that virtually all adhesives can be debonded with this technology, and also you don't have to have any special additives or any special adhesive to cause that debonding. However, substrates have to be thermally conductive materials, and of course, when we are talking about heating in ovens, that means there is no local heating, so you are risking exposing your assembly to thermal stresses, and of course a little bit of degradation of the properties. Debonding by induction, the principle here is you heat your adhesive joint when you expose it to high frequency alternating magnetic field, and the heating itself is done via a combination of the Joule effect and the hysteresis losses. And of course, when you heat up the adhesive, you can apply force afterwards to do the debonding. One of the good advantages of this method is that it can achieve very high heating rates. So you can, in theory, or in practice even, have the debonding in minutes or even seconds. This method can also provide local heating, so you have lower risks of thermal stresses. But the limitation here is that you have to have conductive substrates for this method to work. If your substrates are not conductive, then you have to modify your adhesive with certain additives. You can add, for example, conductive particles into the adhesive. But of course, when adding particles into the adhesives, yeah, this will affect the mechanical performance of the joint in a negative way, of course. Thermally expandable particles, these are actually particles that are made up of liquid hydrocarbon encapsulated in a polymer shell. And when these particles are heated, the liquid hydrocarbon turns into gas and starts expanding while stretching this polymer shell. These particles can easily increase more than 5 times their initial volume, and in the industry, they actually call it foaming agents. The good thing about these particles is that they can be heated up by any method. So here we can, for example, combine induction technology with thermally expanded particles. Also, this method works only with heat conductive substrates and relatively low temperature curing adhesives, because these particles, they need to be triggered at certain temperature, and you want to avoid this temperature when you are curing your adhesive. Of course, we are talking about particles, so that means particles has to be mixed with the adhesive, and this again impacts the mechanical performance of the joint. Then we have debonding by electrically debondable adhesives, and the principle is very simple. You apply an electric potential between two conductive substrates, and then you can have clean debonding at either interface. This is a very interesting debonding method, of course, but it needs a very special adhesive that is patented by a laboratory in the US called EIC, and it's relatively difficult to get your hands on this adhesive. It's not really sold in Europe, but nevertheless, it's a very interesting debonding technology. Here, of course, it only works with conductive substrates. So if you don't have conductive substrates, you have to use a pre-bonded patch between your two non-conductive substrates. Another method is debonding by UV light, which is done by inducing switchable molecules by UV light to cause debonding. This technique is actually used on a commercial level in semiconductors and medical industries, as you see from this little clip, but not on a structural scale. The efforts to produce similar adhesives for structural applications are still at low technology readiness level. Of course, this method needs at least one transparent substrate for it to work. Last method we have is the microwave debonding, which include heating the adhesive by dielectric heating using microwaves. And again, here the heating is above the gas transition temperature, and you have to apply force to cause the debonding. Similar to induction, this methods also provide very high heating rates and can debond almost all adhesives. However, they cannot work with metal substrates because metals, they shield microwaves, and we also have some risks of microwave leakage or long exposures of microwaves. Yes, so to compare these debonding methods, we prepared a kind of a scoring matrix, and here we compared the methods with certain criteria, such as, for example, debonding times, scalability, commercial availability, safety, and overall complexity, and so forth. And we gave each method a non-weighted score. So here we tried to be as neutral as possible to the final applications. Of course, if you want to consider certain applications like automotive or construction, then the scoring will change. Finally, we can see that we have three winning debonding methods, which are the induction, thermally expandable particles, and convection. And we have two runner-up methods, which are the UV debonding and electrically debonding. So if we would like to have some take-home messages from the story of debonding, we can say that induction, convection, and thermally expandable particles, they are the most promising in terms of thermal-based debonding. In terms of heating rate, induction would give the most efficient heating method for thermal debonding. And in terms of strength, then convection would be the best because you don't have to change your adhesive formulation. Now I give the word to my colleague, Jeroen Jordens, to give you a little bit some digitalization aspects in adhesive joining. Jeroen?
Yeah, thank you, Ahmed. So I'm Jeroen Jordens. I'm also research engineer at the Joining and Materials Lab, and I will talk about how you can apply Industry 4.0 and digitalization aspects to the adhesive joining process. So in our lab, what we do is we do research on 3 phases. So starting from adhesive selection and bond design through process parameter optimization, where we optimize the bonding process, up to process upscaling, where we look at, okay, how can you now apply an adhesive via industrial robots? And what we want to do with this digitalization is shorten the cycle from adhesive selection to process upscaling, because typically it takes a lot of time, a lot of effort and costs to do the whole process. And we've done that by connecting all the different steps and all the different equipment to the cloud. And we want to create digitized process knowledge from it. And by doing that, we want to tackle some challenges. The first one is that process optimization flow is very case and customer specific, meaning that if you have an optimal solution for one company, you cannot simply reuse it for another one, even if they use the same materials and they will have the same bonding process. It can be that they just order their materials from a different supplier, and because of that, the surface condition is different, and you need to have different process steps. Also, the data in the past, it was scattered and could not easily be systematically reused in new cases. And also doing real optimization experiments is costly and time consuming. So therefore, we created the following data structure, where on the one hand, we worked on the sources. So the idea there is that we could generate more data. So we connected all the existing equipment to the cloud, but we also installed new sensors like a temperature and humidity sensor in the lab, which monitors constantly the temperature and humidity. And also we created digital work instructions. So these are the instructions that you typically have for the bonding process. And what we did was we generated a system where we can, on the one hand, configure the work instructions. Like here, you can configure which materials you want to join. You can also indicate, for example, for the plasma treatment that we do, what power, for example,
someone
should be
mute
used.
you, I guess. Can you please unmute?
What? Can you repeat? Everything okay? Okay. So yeah, here you configure the work instructions, and you send it to the Proceedings Cloud, which is a system which has been used to show all the instructions. And then they can be shown in different ways. We selected here a tablet, and then the operator can view the instructions, like here, okay, check the machine availability. And every time the operator clicks, yes, I've done this, then a timestamp is saved. And the nice thing is that you can get extra information, for example, of how long every step takes, which can be interesting for the production planning, but also you can link it to different sensors, etc. And here you can also ask additional info like pictures, or if something goes wrong during the process, the operator can add a note and take pictures, make movies, and etc. And you can also ask questions like here, which type of fracture do you see? So yeah, these work instructions allow to gather more information than what you would typically gather during instructions on paper. The next thing that we did was is to create a kind of a cloud-based system where we store all the data in a cloud. We selected Azure, but you can have different clouds. And then we have 2 systems, applications and an ad hoc analysis, which make use of the data. And the difference is that applications typically they use the same type of data. So it's like a dashboard, or you have a model which typically always uses the same input data. For ad hoc analysis, there's a little bit different. There, the idea is that sometimes you want to look for correlations to, for example, see if you can find a correlation between the final product quality, like the break stress of your samples, and one of the process parameters, but you don't know in advance which one and which data that you need. And therefore, we created a knowledge graph, because we saw in the past that typically 80% of the total time you need for this exercise is spent on finding the right data and transforming the data in the right format. And that's not something where a domain expert is very knowledgeable about. So that's why we built a tool, the knowledge graph, which can support with that. So it's a kind of an interface between, on the one hand, the domain expert on the right, and all the data in the different databases on the left. And the idea is that you can ask a very high-level query language. And by doing that, you can get all the data that you need without have to worry. So in the following movie, you see an example of our knowledge graph. It's a very simple example. So you have samples, which are the parts that are being glued together. You can see what adhesive application step was being used to create one sample, also which substrates were used, what treatment conditions were used, and you can also view, okay, what were the exact values, and also if you click, for example, break stress, you get an histogram of all the break stresses that has been tested and that are in the database. And then you can easily also look for correlations, but these are very high level correlations. The main interesting part is that if you look at the right bottom, you can see an example of such a high query language. So it's a very simple query language. And if you use that in, for example, Databricks or Python, you can get all the data and then do more advanced statistical analysis, which is more useful. But the nice thing is here that you don't lose time with looking where is all the data and in which format it is. So you can easily see what data is available and you can easily get the data. That's the main advantage here. And then the last application that we built was a Bayesian optimization model. So it's an AI-based model which help you to find the optimal process settings with the least amount of experiments. So the idea here is that you first load an initial set of data to the model. So if you look here, you can already from the tool get an idea, okay, what are the initial experiments that I should do? Then you perform them, you fill in or you complete an Excel file, you upload it to the system, and then you will see that this will be loaded to the model, the AI model, and then it will reason, okay, if I do an optimization cycle next, where are the most interesting points to search or to experiment for? And then you can even differentiate between, okay, I want some points for optimization, so look for the maximum break stress, for example, and I want other points, for example, for reducing my uncertainty on my model. Because if you click query, it will propose some points with some settings that you should test. And it will also explain or tell you, okay, this is, for example, the strength that I expect for this settings. And this is my uncertainty on my prediction. So that's a nice thing. And by doing that, so we tested this for 2 industrial cases. We could achieve a 40% reduction in the budget to find this optimal solution for both cases, while we had a similar break stress compared to the benchmark, which was just optimization procedure with an expert. Yes, just the normal way or the traditional way. So just as a conclusion, what are the advantages of this digitalization? So you can get more data, like timestamps, pictures, operator feedback. The data looks also structured in a structured way, so you can easily reuse it in future processes and search for correlations. And you can save time and experiments to find the optimal solution. So also a significant reduction in the optimization cost. So then we're moving now, I think, to the end, and we can move to the closing and Q&A. So Gabriel will take.
Thank you, for your presentation. Thank you, Ahmed. So now, if there are questions, please raise your hand and talk. In the meantime, for the people who doesn't have questions, you can please scan this QR code and provide us with your vision on. We want to identify what are the challenges that you have in your company to implement lightweight solutions, and provide us with the feedback of the webinar. So what you will want to learn in the next webinar, what you liked, what you didn't like, and so on. So the floor is on yours. So if you have questions. Okay, if there are no questions, I think that we can start closing the webinar. Again, Thank you again for participating, and please don't forget to scan this QR code and provide us with your feedback. The feedback is very useful for us to develop new webinars for you. Thank you.